Good day, students. The topic we are treating in chemistry now is solubility. Solubility. And under that, we'll look at the definition of solubility. We'll look at the types of solution with respect to solubility, whether a solution is saturated or not saturated. And so I'm going to define solubility first. Solubility of a solute is actually a measure of the solubility of how soluble two or more solutes are in water. So in solubility, we try to compare the solubility, the rate of solubility, or the rate at which solutes dissolves, different solutes dissolve in water, when trying to compare their solubility, because it is different. The solute is possible for solutes to differ in their rate of solubility. And so what is solubility? Solubility of a solute in a solvent at a particular temperature actually is the maximum amount of the solute in moles or grams that will saturate 1 dm cube of the solvent at that temperature. Now, in solubility, we consider some factors like temperature. That is, at a particular temperature, different solutes. Don't forget what I mean by solutes. I taught you in the first video that we dissolve solutes in solvents. Different solutes have different solubilities at different temperature. Now, and at the same temperature, different solutes have different solubility. And we consider the mass of the solute that dissolves, and the volume of the solvent, that's a liquid, that is used to dissolve that. Now, the solubility of a solute again is, the solubility of a solute in a solvent is at a particular temperature is the maximum amount of the solute in moles or grams that can saturate, or that will saturate 1 dm cube of the solvent at that temperature. 1 dm cube is like 1000 cm cube and is the volume of water. The solubility of a solute in a solvent at a given temperature is a maximum amount in moles or gram of the solute that will saturate 1 dm cube of the solvents at that temperature. And so we have different kinds of solution. We have a saturated solution. We have an unsaturated solution. If I dissolve a certain mass of salt, look at this, in water, and I take double of such salt in another container, I'm going to add virtually the same quantity of water to this. I will do the same here. Now, by the time we stir these two together, we will notice that this salt, because it contains less quantity of salt, this will dissolve totally. We are assuming that we have the same quantity of water. Now, by the time I stir this contains double of the salt that this contains, despite the fact that they have the same quantity of water. Now, this solution can still hold more salt because it contains less. It can still hold more salt, while this is almost saturated but not yet saturated as well. Now, it shows that this is not saturated. This is an unsaturated solution. It can still contain more salt. I'm going to demonstrate that. An unsaturated solution is one that can still dissolve more solutes at a given temperature until it becomes saturated. That is, at a given temperature and at a given at a given volume, for a given volume of water, there is a certain level of solubility, or a measured mass of a solute. Now, these two, they are having the same volume of water but different mass of salt. This has less salt, while this has double of the salt in the same quantity of water or the same volume of water. Now, I'm going to see the one that can take more. I will add more to this and also add more to this. I'm adding again, and I'll add to this. Let's stir. You will notice that the solution, the volume of the water did not increase, but the salt increased. Now, by the time I continue stirring this, because this has less water, at the beginning I added just 1 spoon of water, and I had 1 spoon of salt, and I added 2 more. Here I added double at the beginning, and I added 2 more. If you take a close look at the two, you will notice that this one, as the first container, has finally dissolved, and it was able to dissolve all the salt, while this is still having an undissolved salt, showing that the solution is already saturated. Because I didn't increase the volume of water, this can no longer dissolve any salt again. It has dissolved the quantity, the maximum quantity of salt that can be dissolved in it has been reached, while this can still hold more. Until you have an undissolved salt, a solution is not yet saturated. So an unsaturated solution can still hold more salts. So I will define an unsaturated solution as one that can still dissolve more solutes at a given temperature until it becomes saturated. Why? A saturated solution is a solution that holds as much solute as it can dissolve in the presence of undissolved solute particles at a given temperature. In the presence of undissolved solute particle at a given temperature. In that case now, the undissolved solutes and the dissolved solutes are in equilibrium. They are in equilibrium at a given temperature. Now, how do we get a supersaturated solution? In this case now that we have a saturated solution, if I heat this solution, I can still force the undissolved salt to dissolve. By the time I heat this solution now, the undissolved salt will be forced to dissolve in the solution. But the problem is that at a point it can settle when it cools, when the temperature begins to drop. When the temperature begins to drop, the quantity of salt or mass of salt that was forced to dissolve finally, when the temperature of the solution begins to drop, it will come out again to solidify again and crystallize out as salt. So a supersaturated solution actually is one which contains more of the solutes than it can normally hold at that temperature. A supersaturated solution is a solution which contains more of the solutes than it can actually hold at that temperature. I define a saturated solution as one that can hold as much solute as it can dissolve in the presence of undissolved solutes at a given temperature. While in an unsaturated solution is a solution that can dissolve more solute at a given temperature until it becomes saturated. A supersaturated solution can hold more of the solute than it can normally hold at that temperature by heating the solution. And so from here now, we determine the solubility of a solution using a curve. We have what we call solubility curve. But what is solubility in this case now? Solubility of a solute in a solvent at a particular temperature is the maximum amount of the solute in moles or grams that will saturate 1 dm cube of the solution at that temperature. That will saturate 1 dm cube of the solution at that temperature. Now, what's solubility curve? Solubility curve actually is a graph showing the different solubilities of different solutes at different temperature. It shows the solubility of different solutes at different temperature. It is a curve of the solubility against the temperature of different solutes, different salts. Now, on the x-axis we have the solubility, which is in gram per dm cube or mole per dm cube, and we also have temperature on the y-axis. This is a typical example of a curve. You can see on the y-axis we have this is the y-axis, we have the temperature, y, this is the solubility. Now here we have different salts. The first salt here is calcium tetrasulfate 6. This is potassium triacylchlorate 5. This is sodium chloride. You can see the solubility is 40 gram, and at temperature 10, the solubility of sodium chloride is constant. When it's 20 degrees Celsius, it's still almost constant, almost straight, and it only increases slightly here. When the temperature is increased to 90, it increased to like 42 or so. Now, let's look at another curve here. You can see this is potassium. All right, let's look at sodium triacylnitrate 5. Look at the solubility. The solubility is 70 here. Okay, 76 or so. Now at temperature 10. Now as the temperature increases, normally solubility of a solid increases with increase in temperature. When you eat a solid in solution, the solubility will increase. The solid will dissolve easily in solution. Unlike gases, the solubility of gases decreases when you increase the temperature, because as you increase the temperature of gases, the particles will be free and will not be settled. So their solubility will decrease when you increase their temperature. Although hydrogen chloride gas is an exception. Now look at this. I just said something that increase in temperature, increase in solubility. This is a typical example. Now, as the temperature, which is here, increases from 10 to 20 to 30, you can see the solubility increasing from 78 to 80 to 80 to 90 to 180 of sodium triacylnitrate. So this is a typical example of what we are talking about. Another one is here. You can see the solubility increasing from 10 to 20 to 30 as the temperature increases. This increases here. Then we also have potassium triacylchlorate at temperature 0. The solubility is less than 10 here, and as the temperature increases to 10, the solubility increases to 10, 12 to 20 here now. When the solubility is 20, the temperature is 50 degrees Celsius, potassium triacylchlorate, and sodium chloride is soluble whether you increase the temperature or not. At temperature 10, the solubility is almost the same, even up to 90, until it's only increased slightly. And that of potassium chloride too, because most chlorides are naturally soluble in water. Now, what are the applications of the solubility curve? What are the uses of the solubility curve? The applications. Solubility curve enable pharmacists to determine the amount of solid. It helps them to determine the amounts of solids that can be dissolved in a given quantity of solvent to give a prescribed drug mixture. Take for instance the preparation of your suspension. When you buy drugs, suspension for instance, they will tell you, okay, 100 milligram dissolving so amount, maybe 50 ml of water to make 100 ml for instance. Now it helps them to determine the amount of solid drugs that must be dissolved in a given quantity of solvent. The course also enables chemists and researchers to determine the most suitable solvent to be needed to be used at various temperatures. They know the temperature at which different solvent works, and so they determine the solvent, the best or suitable solvent for the extraction of essential chemicals, for instance now, or from various natural resources. And with the help of the solubility curve, a given mixture of solutes can be separated or purified by fractional crystallization without destroying the salt. When a saturated solution of such a mixture is cooled, those fractions with very low solubility will be the first to crystallize out truly out of the solution, while those that are still within the limit of solubility will remain in the solution. So what are the deductions from the solubility? I told you, I've explained that the solubility of potassium triisochlorate and potassium triisochloronitrate 5 increase very rapidly with increase in temperature, while the solubility of sodium chloride and calcium hydroxide, even potassium chloride, are independent of temperature. They are not affected by temperature. So sodium tetrasulfate shows a solubility curve with a sharp break at a point. Then we have all temperature between 0 degrees Celsius and 100. At all temperature, calcium hydroxide has the lowest solubility of the 6 compound, for instance now, or potassium chloride. The solubility of potassium chloride increases at a constant rate with the rise in temperature. Let's look at this curve again to see what we are talking about. You can see. You can see that of sodium triisonitrate 5 increases sharply. That of sodium chloride, potassium chloride is independent of temperature. That of potassium triisochlorate increases steadily, and that of calcium sulfate decreases. Calcium tetrasulfate 6, with increase in temperature, the solubility decreases. Thank you. And in the next video, we are moving to the calculation of solubility.